Where to rock?
Yeah.
Cool.
Let's go.
So yes, so today we're going to talk. Hello, I'm Julian. For those of you who don't know me, I can see that many in the crowd do know me. So, but yes, I lead the formal verification team at Nethermind, and I guess these days we focus very strongly on ZK related stuff. So both like constraint verification, witness witness generation verification, as well as like functional correctness, but also then the underlying proof systems, right? So we've been working on with the arclib efforts to formally specify Fry, which I think Kwong will be telling you about a little bit later today. So getting obviously the feedback from all of you guys who, hopefully, well, there'll be some people who know more about Fry than us, and we'll be able to fill in some further generalizations or whatever, we'll see. But yeah, as I said, today I'm going to be talking about end-to-end formal verification here, specifically of what is required for L1 proving, right? And so I have sort of this, oh, no, I don't. Wait, I want to go to the next. There we go, excellent, cool. So we have here sort of an overview of the trust base, which is actually required as part of the, that will be sort of added in, I guess, as part of the L1 proving effort. I mean, some of these obviously were sort of already there before, and so we won't be talking to, and people have been working on sort of this to a large extent for some time, so verifying solidity, Yule, and these other things. We'll do a very quick overview of that. But in particular, with respect to verification, these particular solidity and Viper don't have actually any formal semantics, so formally verifying the compiler for the moment is not really possibility, which is why.
So you're missing potentially an arrow as well.
Sorry, am I?
Potentially between EVM bytecode and RISC-V execution clients.
Yes.
Because you have to lower to RISC-V now.
Yes. Fair point, actually. Fair point. So So okay. I guess that would be an extra arrow that would be added in. I don't know if I'll be able to quickly add that into the actually, well, anyway.
If you want to take a marker and...
Yeah, exactly. But anyways. But then on the, what do you call it? But then, yeah, so the rest of this, though, is a little bit more interesting, and we'll be going into a little bit more depth there. So obviously we have sort of like traditional implementations of execution clients like ref, geth, etc. that we may want to. Sorry?
Nethermind.
Thank you. Very important. Very important. And
which compiles to RISC-V now?
I've heard. People tell me. So there you go. But yeah, Nethermind client, and in fact, a number of mining clients that I discovered while searching about this I hadn't previously heard of. So there you go. There was also Besu, which I didn't know about too much. This is apparently one that's used by a lot in industrial banking context. But yeah, I was sort of interested to learn a bit more about that. But yeah, so obviously we would want to verify these. We'll get into details of how. Then obviously these will be kind of compiled. We'll need to compile from whatever language they're written in, and we'll see that those are primarily really like Rust, Go, C#, if you're like counting the Nethermind client, and a number of Java, in fact, right? And obviously we would have to, so we'll want to verify those. We'll want to have a verified compiler to RISC-V, essentially from that, right? To really have end-to-end verification. And then this RISC-V execution client will obviously then, everything here is, I tried to add this in ticks and I got all sorts of weird stuff happening. So I eventually gave up. No, it's meant to be a dotted line around this that says RISC-V ZKVM, right?
Question.
Sure.
So first question, this solidity bubble, does that represent like some particular solidity contracts, or what does that represent?
So I mean, it's just that we're just representing here sort of the flow of dependencies here, and it's saying that yes, you would write a solidity contract, you would compile this down to EVM bytecode, right? This would be executed on an execution client, which would then be for which we then like generate a ZK proof inside of a RISC-V ZKVM.
Okay.
Right. That's sort of like the flow that this is trying to represent.
Okay, That represents whatever particular solidity contract.
Sure, exactly. And as I said, really one of the key issues here is that none of these things have any formal semantics. So, but this is actually kind of fine in the sense that, if you really want to, particularly with solidity, you can compile this down to EUL, and then EUL does have a formal semantics, which we'll talk about a little bit later. And the EUL to sort of EVM bytecode pipeline is a lot sort of shallower and simpler than obviously going all the way from solidity to EVM bytecode. So actually verifying such a compiler is much more plausible than, say, verifying sort of a Viper compiler or something like that.
Okay, thank you.
Right.
So second question.
Sure.
Is the distinction between a verified compiler and a verifying compiler in play here yet?
No, not, so I'm just talking about a verified compiler, as in like one where we verify semantics preservation. So we have the semantics of the language we're compiling from, and we have the semantics of the language we're compiling to, and we prove that the compiler will sort of preserve this, if that makes sense.
Okay, sure. So I'm just wondering, would it suffice to have a verifying compiler, i.e. one which constructs, along with the object code that it produces, a proof that it preserved the semantics in that particular instance? Or do you suppose we need to prove a universally quantified state?
Fair. Oh, I see.
So I think in the case of smart contracts, because you're interested in fairly arbitrary smart contracts, you probably want a verified compiler rather than a certifying one. Typically, when you're interested in a certifying one, you're okay with restricting yourself to a subset of code.
Okay, fair enough.
I see. Interesting. I didn't quite realize what you meant by a verifying compiler, but certifying is a compiler. I see. So now I understand what you mean. Obviously both of them at the end of the day, as long as you have a proof, obviously, of a verified compiler, or your certifying compiler outputs a certificate. In both cases, you're certain of the semantics preservation, right?
Right.
So those are pretty. The outcome is equivalent with respect to knowing that the EVM bytecode is equivalent to your high level, whatever your high level.
Right, yeah. The difference in practice is going to be if you have a verifying compiler that's not a verified compiler, then maybe at some point one of your users will run into an issue of like, hey, I have a perfectly good program that your compiler tells me it can't prove the compilation of.
Yeah.
So I think it's also the best example of a certifying compiler you would find in our industry would be the Cairo compiler. But what it only outputs proofs for certain programs for which they have pre-written specifications in Lean, for example.
Yeah.
And so it works with a pre-compiled and nothing else.
Oh, right.
Because otherwise it would prove something about the compilation of a program, but it would have nothing to prove against. For most things, because there would be no specification against which is verifying that the compiled program is equivalent to. Because otherwise, if you have a certified compiler for every program, you have a verified compiler essentially.
So does certifying compiler mean something different from verifying compiler?
In my mind, they're the same.
So I didn't know the term verifying compiler. I know the term certified compiler, but I'm assuming these are equivalent, right? But what we mean here is something that outputs a proof that the high-level code is equivalent to the outputted code. Yeah, we agree on that definition?
Yeah, I think
excellent. Okay, excellent. Good. Cool. So where were we? Yes. So were there any other questions before?
Those were my questions.
Okay, excellent. Yes, so we've covered this bubble. We've talked a little bit about this. And then, of course, we basically would end up, if we wanted to execute a specific solidity, like a specific contract in a certain context, we would end up basically throwing both of these in, and this is the pipeline that we're currently, that the Ethereum Foundation is currently targeting, which is both of these would be thrown into the sort of witness generator. As I said, all of this is now sort of the RISC-V ZKVM bubble. So these would end up being thrown into the witness generator for some RISC-V ZKVM, be that RISC-0, succinct, whatever, right? This would then essentially execute we would then generate essentially a trace of the execution of our execution client, right? And then this would obviously get, the trace would then be passed to the snark prover, which would also receive a set of constraints, right, which are meant to verify, well, these constraints are meant to imply essentially the semantics of the RISC-V ISA, right? And then obviously this prover would output a ZK proof, which would be verified on the snark verifier, which in turn obviously also needs to know the constraint set. Yeah, and so obviously this itself involves a new set of statements that we need to verify. So of course we want to know, most importantly, because this is what enforces the security properties, right? The most important part of this is that obviously the constraints generated imply the RISC-V semantics, right? And that the snark verifier is sound, right? So with those two properties, we know enough to know that the system now enforces the security properties that we design, right? Of course, there are still all sorts of things that can go wrong here that would which would affect the sort of liveness of the system. So for example, the witness generator could be buggy, it could generate invalid RISC-V traces that the constraints wouldn't accept if they were verified, right? And then of course we could have the snark prover also being buggy and generating for certain inputs proofs that will never be, oh, sorry about that. Yes, excellent. In fact, I've got enough battery to finish this talk. Excellent. So yeah, so basically there within this bubble, there are two sets of properties that we want to verify that are sort of broadly partitioned into this enforces security properties and this enforces the sort of liveness properties that we want. So yeah, so now I'm just going to sort of start going through these things one by one, looking first at the verification of these execution clients, right? And then we'll look very quickly at specifically verifying constraint systems for RISC-V, well, constraint systems generally, and then we'll look specifically at constraint systems of RISC-V ZKVMs, and then we'll talk very briefly about the verification of the underlying proof system. Kwang will be talking about this at much more length this afternoon, so I won't give too much detail. Cool. Okay, so obviously the first thing if we want to verify an execution client that we're going to need is a formal semantics of the VM, because we need to know, hey, we need to have a specification for this thing, right? And obviously in the case of a VM, the specification is often, but not always, going to be somewhat complicated, right? And so these are sort of the main EVM models that exist. So obviously there's the KEVM model developed by Runtime Verification, which is quite interesting. Obviously it's mostly targeted at the K verifier, and I don't want to obviously I can't speak for everyone in the room, but personally looking at K semantics for me is they're not very easy to decode a lot of the time, right? And now there are experts. We have someone on the team who used to work at Runtime who worked on K quite a bit, who just looks at this and understands it, but they're not the easiest to understand. But actually, Runtime has recently been working on a K semantics to lean extraction, and so now they've extracted their KEVM semantics into lean. And interestingly, they have been working on actually proving equivalence with this with our EVM UL model in lean.
They haven't made that much progress.
Yes, yeah, I talked to Juan recently, and I think essentially the issue is that the extracted lean is very difficult to work with, essentially.
The extracted lean is kind of difficult to work with, but you also actually have a lot of things that you represent differently to them.
Yes,
so there's a lot of wrangling in proofs, and then beyond that, like gas safety proofs are basically
what gas safety? I see. Yeah, fair enough. Although, actually, but sorry, why are gas safety proofs a no-go?
Just hard in general.
Fair enough.
And actually, the same for when they're trying to verify the EVM interpreted to RISC-V to gas safety proofs at nightmare.
Fair enough. I see. Yeah. Yeah, I mean, obviously we saw, so I mean, I'll mention a little bit of our experience. So we developed this EVM UL model, which is, well, like all of the others, in fact, is executable. And so we actually executed it again. We ran the execution client tests with it, right? And in fact, it passes 99.99% of them. And in fact, the two tests it doesn't pass essentially are tests where I think the discussion was essentially that they were buggy tests in the sense that the test itself included an error outcome that wasn't actually no one was able to give us semantics for. Like no one knew what this.
We have a lot of new tests now.
Excellent, wonderful. Well,
related to zkVM.
Oh, really? Okay, fair enough. So we should look at obviously doing that. But yeah, so our EVM Mule model though is only Cancun compatible. We're hoping to, in the not too distant future, work on upgrading that to also be Pectra compatible and perhaps. Sorry? And Fusaka, yeah, of course, and Fusaka, of course. And obviously passing all of these new tests. But yeah, it was actually quite interesting in the sense that actually getting most of the semantics right was very quick, without wishing to sound too quick and conceited. It was very quick is maybe strong. Let's say relatively quick, right? The real difficulty in getting all of these tests to pass was twofold, as Alex is pointing out, in the sense getting the gas model to be correct. There are a lot of subtleties there, some of which are not particularly well documented. Which we ended up having to dig through implementations, through the KVM model, these sorts of things to be able to actually figure out. So that was quite interesting. And then, yes, once again, actually the execution tests, the majority of clients out there, they only require that their client passes the execution test insofar as the faulting tests. It requires the test to still fault, but it doesn't actually require the client to match the specific error required in the fault, right? And so we actually held ourselves to an even higher standard, and we required the output of the errors to exactly match what the Ethereum execution client tests required, essentially, right? And that, as I said, this was very much an 80-20 problem, where getting most of the semantics right was like pretty quick, relatively quick, but then actually overcoming this, getting the test errors to come out perfectly, and getting the gas model to come out perfectly was pretty hard, but we got there eventually. And then there's also some work at KTH on a ROC EVM model. Okay, or not?
Nothing worth talking about, yes.
Yeah. No, I wasn't. I know there's ongoing work on. Oh yes, go ahead.
Wasn't there something in Daphne as well?
Yes, there's a model in Daphne, but it's
not
not maintained. It was also not that useful. And then there's a partial model in ACL2, which will actually be completed soon. And then there's also a partial model in Hall 4, which may get completed soon.
Yes, fair enough. Okay, so I wasn't aware of the progress on the Hall model. So these ones were the ones that I thought were sort of progressing / already at relatively high specification compliance, or test compliance. It seems there are a couple more. But yeah, I mean, I'll be interested actually to see, particularly with ACL2, what the outcome will be in terms of what we'll actually be able to verify with this. But yeah, so we need some formal semantics of the EVM. These are some examples. There are a couple more that I missed. And then, of course, we're going to need a model of the language that the underlying execution client is written in, right? And as we said, well, Rust, Go, C#, and Java are the main ones. For the moment, out of all of these languages, Rust is really the language with the biggest formal semantics effort, right? Effort to actually have a full formal semantics of the language. The other ones, I mean, I know there's like a Go formal thing, which seems to have been dead for a number of years now, to be honest. I don't know if anything is happening there. There have been some sort of like .NET formal model. There has been some formal model work on .NET, but pretty older versions, not with new versions as far as I've seen. And then I know there's a KJava thing, but it was for like Java 1.4, and I don't think any updates have been done since. So really, out of all of these languages, the easiest to target in terms of actually having a formal model of the underlying language is really Rust, right? And that is really what this program has been targeting. And there are there's a bunch of tooling
Chris
here.
Jones was a Y, we should say.
Oh. Okay, I will actually take live practice. 2 seconds.
It's fine. I don't think they'll be watching this.
It will literally take me 2 seconds. So okay, my bad. There we go.
And Aeneas is also with the.
Well, it's surprising that Java doesn't have formal verification harnesses, because Java has the best specification
Yeah.
of the.
They're too busy doing homotopy type theory instead of doing formal semantics for Java.
Wait, what just happened? Okay, I think it's randomly skipped to another slide. Okay, there we go. Cool. There you go.
Yeah, so Aeneas was the other one.
Wait, is that how that's spelled?
Aeneas.
Okay. Great. Aen.
Because I think you can also pronounce this Aeneas rather than Aeneas. I've never known how to pronounce this. Oh, that's on Wednesday.
Aeneas, you say?
Yeah. So A instead of U. There we go.
Okay.
All right, we've got the slides type check now.
Thank you. Excellent.
Can I flag a concern I have about this?
Yep.
I think this is flashing boondoggle to me because of this last sentence. So currently the Rust compiler consists of about 5 million lines of C++ code.
That's correct.
And about 1 million lines of Rust code, something like that.
Sure.
This I don't think is feasible to do within the budget of $20 million.
That's completely accurate. Yeah, completely.
So we're saying that we need it, not we are.
I'm not.
I'm going to say that we don't need it. I think what is a more viable approach would be to create execution clients in such a way that we thought about how we're going to prove them correct from the beginning and construct it.
So this is actually the idea with the rock one, which is that actually it'll compile through certificate.
Yeah.
Oh, so you're going to extract the Rust to cock? Is that the idea?
No. We're writing. There's a client being written in rock, which will be compiled down to this file through certificate.
Okay.
So nothing involved other than rock and certificate.
Yeah. So that's an alternative means that. So I think
but
that.
It'll be slow.
I think that the focus on Rust was particularly in the context of the DARPA certified Rust compiler project, which is now dead. Sorry.
Right, but it's not dead because it wasn't working. They were actually making good progress on that. The president came in and did.
Yeah. So this was a political decision, not a technical one.
I think. So I mean, there is a point, which is of course, should we try to think of do we want to do fully verified general purpose compilers for languages like Rust, which are going to be obviously huge tasks that would involve many years for many people, or are we okay doing perhaps verified compilers which are highly domain specific, because we are dealing with mostly domain specific code for most things.
Yeah.
You could just use a simpler language, like NIM maybe could be a good choice.
But then it's the idea saying that I spend the next year of my life basically becoming a NIM evangelist, so that every client emerges into NIM.
Well, I don't think you have to sell outside people on NIM. You could just be here, we're gonna make an execution client in NIM and the very.
But there is an execution client in NIM.
Oh, well, okay.
It's just not widely used.
Right.
That's the issue.
Well, there is already a verified C compiler. Or we have to do
but using Concert is not worth it. I'd rather have bugs than use Concert.
It's proprietary. Is that allowed within the constraints of EF?
It would be an issue. Actually, it's also so the licensing is one issue. I'm not even sure how it would work, because also we have to give clients that people can build from source. So everyone who wants to do that would have to pay a license.
So that doesn't work with
which is a huge blocker. The other thing also is that it uses C99. So you would have to go and you're not even running very modern C code.
And then your execution client is in C. I talked with interviewed a guy who worked for the Department of Defense proving correct C code that is used to launch missiles and things of that nature. And what they were able to accomplish was like, I want to prove this program terminates. I want to prove this program doesn't run out of memory. Like it was very like laborious work with kind of rudimentary results.
Yeah, these are multi-year projects of one program. I can give you a number. So there was a discussion at some point of do we want to get CKZG formally verified, right? And so the issue here is that people are using CKZG instead of ProKZG or RustKZG. But anyway, people are using CKZG, and the EF said you can use it for the next. I guess there's 2 more years that they can use it, I think, before they finally move on to Rust and Go. There was a proposal to do preliminary work to formally verify this, and the proposal to do preliminary work to formally verify this was $1 million.
Well, sure. Like when you have C code, like it could buffer overrun. It could do all kinds of crazy stuff that you have to rule out with ad hoc proofs in each instance. Whereas if you just write a programming language that has more protections built in, then like like you could for example write in a language where all programs are guaranteed to terminate, and then prove every single program terminates. You just know that.
Yeah, the thing is, but once you want to optimize, you still use some safe Rust, for instance.
And then also the trade-off is that, okay,
but
the
the
language
thing is, the unsafe Rust is clearly delimited, and you have tools to formally verify.
So we discussed with the Zing team, and they have issue with Rust due to building Rust, the generative code size, the fact that when you try to merge everything into a static library, you have symbol conflicts. And the thing is, CKZG for 844 is a very restricted set of C. There is no array accesses there is no buffer overrun, there is no almost zero memory allocation because the blast library inside can be run on TE, and on TE you don't have malloc, so everything is stack-based. And on the KZG side you have some malloc, but it's very, very restricted. And also, Blast has a formal implementation in Galwa, crypto.
Yeah.
So,
but crypto is unusable.
I wasn't a fan of what they did.
No. So Galwa was, when I said like $1 million for like preliminary work, that was Galwa.
Okay.
And it was for you, and then said then you're locked into crypto, which means you're locked into Galwa. So they're very good, but there's a lock-in effect, which is not always desirable.
Okay. But for me, C is fine if for cryptography, because to write cryptography code, you need to restrict yourself to avoid a lot of memory application, you have this, etc. So you don't run that much into those buffer overflow, etc.
Well, but in each instance, right, every time you do an array indexing, you would have to prove that you didn't overflow the buffer, or no?
But you don't have arrays in Blast, for example. You do have those in KZG.
But the thing is, so once again, you do have to get back things like what I was saying. Because we are doing in many cases something that is highly domain specific, you can write domain specific compilers, which are then much easier to verify. Whether you're using C or something else, right?
Yeah, in any case, like a range check is like the very first thing anyone that does SMT solver or formal verification implements, because it's easy to add invariant or precondition, post-condition that accesses are within the range. So to me, that's not a blocker. And even on the Rust side, those accesses are not proven at compile time. You have a runtime error.
That's true.
But we're also using Rust because people use Rust. Right?
Yes.
Like the Rust pre-exists, this whole idea is fully verified.
You have actually a connection with Z3 that actually does verify this through SMT solver, that our accesses are can be compiled away without the exception.
Yep.
Okay, nice. Where was I? Yeah, so debatable whether this is the right way to go, clearly. So,
But I think it is in the sense that currently the code that we want to fully verify is in Rust.
that's correct.
It
Yes.
is the way to go. If you want to rewrite verify as a NIM, then we'll look at NIM, right?
Yeah. And of course, actually, like a lot of the tooling I was talking about in the previous slide, particularly the snark provers, are also written in Rust. So there is a sort of like, although yes, once again, without the Rust compiler being verified, yes. But yeah, but I mean, part of the advantage of going for Rust tooling is that it has a sort of like a multiple effect where it can be used for the execution client.
And the other thing is that as far as languages like those which are on the slide go, Rust is by far the easiest to verify because you get a lot of like insights from the types which are preserved, right? So when you're extracting Rust to the end of your hacks, the extraction is done from tier, and so you preserve a lot of type information, which is extremely useful when you're trying to do proofs.
Yeah. Yeah, exactly. Cool. So
just one more question. Assuming you get to the point where you have a Rust verified Rust compiler.
Yes.
Like presumably that would just be valid for that particular version that they work on, right? So like when a new Rust version is released, like how much work would one expect to have to do with the
Depends on the release. I think so. One, it depends on the release. Two, it actually depends on the methods by which it is verified. So if you look at traditional, let's say, old school compiler verification, and this is the reason that Concert only works in C99, you have manual proofs for each compiler pass, right? And so if you add a new compiler pass, you have to do another proof. Back in the day, I talked to someone who did her PhD thesis on this. One, like, formally verifying a type of pass would be a paper in a top conference, and that was like 6+ months of work for one person. So this is unreasonable to maintain, and so that's why if you want to use Concert, you're doing C99, and that's it. Now, we now have much better methods to automate these proofs compared to when people doing Concert, which is like 2008, in that era. If you look at some of the work that's being done, for example, on verification of MLIR, by someone who is in Cambridge, actually, who we're going to see on Tuesday, they have proofs which are pretty close to automated. So it's much easier to verify these things. They also benefit from MLIR having these static, which is domain specific, so it seems to be like nicer representations. So it's possible that if you find a way to automate most of the proofs, you can get maintenance, which is trackable. Not within, okay, push button, everything is fixed, but within, for a new release, it's like less than a month or something to like re-verify the compiler. Considering the manpower that go into this, so like with Rust, another aspect is, AWS are huge on Rust verification. They're doing this effort to formally verify the entire Rust, SCD. A lot of other companies are obviously interested in Rust. Google has been, also running along this, like rerunning in Rust just cuts down bugs by half. So this is the reason that there's also all of these tools for Rust verification. And this tool is non-exhaustive. There are like 10 other ones.
Yeah. These are.
So that's also that was also why DARPA had this interest in a Rust compiler, which is that it is heavily used across industry, and that there are, if Microsoft, AWS, Google want a verified Rust compiler, they will have the engineers to maintain it. Which is so that's, I think, like, it's not something to ignore. It's not what's blocking it from happening.
Well, there's also this effort by the Department of Defense to
rewrite it in safe languages. Rewrite C into Rust.
Well, they have standardized on Ada as their safe language, and now they're trying to replace Ada with Rust.
Yeah. So this is quite cool, actually, related to more direction. So the current status of this is that actually now when people want to verify C++ or C code, they actually translate it to Rust, and then they verify the Rust, and then they have a proven translation from Rust to C to get back into C.
Oh, interesting.
That's how bad trying to verify C or C++ is. If you're better off translating it into Rust, verifying Rust, and translating it back. And there's a couple very cool papers about this, actually. That's quite cool.
They use ADA Spark, right? Yeah, they use ADA Spark for verification because ADA Spark is a subset of Ada. And Spark is their for non-verified compiler backend. And then Spark is trying to add some borrow checking. At least they were trying to do that 3 years ago as well, because they formally verified lots of stuff, but not memory.
So maybe the approach is like just make a new Rust compiler that is way simpler than the reference one.
So I would be down to do a Rust compiler for cryptography, basically. And you say, okay, you can use this, like, whatever, functional subset of Rust or something like this, which also happens to work well with ANS. And then well, I can say MLIR, but and then you just kind of lower down, MLIR or something which is tractable as a compiler tool chain to verify. And I think this is why every time you hear me mention MLIR, it's basically because if I have to pick a compiler framework to fully verify, like, it will be MLIR. Because there's just tooling around to do this and a lot of people interested in doing this.
What's the, for execution of lean code, is there a decent story of interoperability? As in, if you wanted to pursue a story of, like, write the execution client in lean and accelerate special, bottlenecks of the execution client computation in something that's faster, is that feasible?
Yes. So, I mean, the performance of extracted lean code is not really...
I think the idea is that you would write a backend to something that's optimized, and then you would limit yourself to a subset of lean, which will say, because I mean, some reasons that, like, lean is slow is depending on, like, your integer type.
Yes, exactly. So lean's, like, basic representations of certain types can be quite inefficient. But, like, for example, the natural numbers, their, like, default representation is, like, piano style, right? But obviously lean has the capability of actually substituting a lot of the type representations with optimized sort of representation. So, for example, nats in runtime compiled lean typically get substituted by, like, some GMP representation, essentially, right? But yes,
I mean, you could, like, we have MLIR data structures in lean, which are actually quite fast. So if you could just write a mapping from your lean code to those data structures, then you would be straight into an MLIR pipeline, and you could make that fast.
Yes.
The question there actually that's interesting is whether limiting yourself to types which are friendly to this would hurt then the proof ergonomics of proving your lean program. But that might be circumvented by running a bunch of intermediary levels.
Plausibly,
So we're back to isomorphisms.
Yes, as always. Cool. So yes, okay. So this is Rust compile. Sorry, I've completely lost the flow of what I was going for, but that's okay.
Yeah, I told you compilers would come up.
Yeah, you did say so. But yeah. Anyways, we'll really see, I guess, what happens with this in the future. We may end up, as you said, maybe targeting a subset of Rust, maybe using some other language. But ideally, we would want some sort of verified Rust compiler, at least for a subset of the language. Although, as Alex pointed out, the maintainability of these things is still, to some extent, an open question. And when talking about this, there's always one story that actually involves Ilya, who sits right there, that I always like to say in this context, which is that I think it's important not to underestimate how much automation has come into proof assistance in the last couple of years, and how much that has sped up. And Ilya already knows now what story I'm going to talk about, and how much that has sped up, like, the rate at which, the speed at which we can write proofs, right? So 2.5 years ago, we were working with RISC-0 to verify some of their core constraint system, and at the time, obviously, it's a RISC-V. It's a constraint that's trying to, like, model RISC-V semantics, and so we needed a lot of theorems about bit vectors, essentially. And at the time, lean had a definition of bit vectors in, like, batteries, I think it was, right? Was it even in MATLAB?
It was.
Oh, it was in MATLAB. Okay. So lean had a model of bit vectors in MATLAB, but it had essentially no associated theorems, right? And basically, Ilya spent about 3 months of his life writing a bitvec library in lean which took a tremendous amount of time, well, 3 months, and on top of that one, also has to account for the loss to his sanity. So, so it was a pretty big impact. But and then the really sad thing is that like 2 or 3 versions of Lean later, they changed the definition of bitvex, which completely destroyed all of these proofs once again. But now the definition of bitvex is fixed, and on top of this, there are a bunch of like tactics that are specifically designed for proving things about bitvectors, right? That use a variety of techniques extracted from different areas, including stat solving and these sorts of things. That means that the vast majority of proofs that Ilya wrote are now a single line, right? Are either already in MathLib or a single line, right? Which is just BV decide, bitvector decide, right? And so I think it's so basically in those 2 years it took.
And bitvectors has carried on improving a lot.
Yes, yeah, exactly. So there's continuous work on this, and the thing is, so basically in those 2 years, it's gone from like it took him 3 months to write this to probably he could have gotten most of this proofs done in a day now, right, or less, right? So so I think it's important to understand that like there have been in the past a number of certified compiler efforts. Oh, damn, sorry. They obviously were extremely tough, took years, had limited results, difficulty with like really having to limit yourself in terms of the compiler, optimize compiler passes, these sorts of things. But this hasn't been done in a bit of time, and I actually would be very curious to see it done again, just because the improvement in automation has increased so much in this time that I heavily suspect that it will be, for some definition of easier than it was in the past. So there you go. Cool. Okay.
Before we move on from execution.
Okay. Yeah. Please go ahead.
One of the interesting things I've heard, I don't know if it's true or not, but I've heard that some of the people in finance, like big banks, are formally verifying some of their software, and they're also formally verifying the hardware that they're running on.
Yes, this is correct.
Sure, yeah. Okay.
So that seems like a necessary step in order to really know that the computations that are actually happening are the right ones.
The hardware part, you mean specifically?
Well, yeah, like
so software as well, because I mean, so Jane Street is a prime example because they use YAML,
yeah.
But a lot of them basically do care about even basic things like time safety, because if markets are volatile and they're getting potentially random streams of data as inputs, they want programs that are not going to, fuck up.
Yeah.
But hardware choice, yeah, I knew when I was hiring, one of the candidates I had actually is going to work on FPGA verification for some headphones, like high-frequency trading firm or something.
Right. So like so in order to have this verified compiler, you would need a formal semantics, yes, for the source language, but also for the target language.
Yeah, which would be RISC-V in this case.
And then are there RISC-V chips that their circuitry has been proven to implement the semantics of RISC-V?
There is
RISC-V.
There is full verification of RISC-V hardware as a thing. Whether there are people who use these chips in production for something is not.
Yeah, RISC-V hardware is not used, like real RISC-V hardware is not used very frequently, of course, in practice. But actually the models that do exist, I mean, a lot, as you can imagine, formal verification is even more popular in the hardware industry than it is in the
software industry.
better. And better, yeah. I mean, there's sort of
the Axiomite would be a company that does in the UK.
Yes, yeah. So I mean, there are reasons that it's sort of, in quotes, better. One of them is that, I mean, hardware is fundamentally a finite state machine, right? And so in some senses, it's kind of easier to reason about, right? But
the other thing as well is this hardware, when we're verifying the hardware circuits, the model is quite different because, for example, for them, an under constrained circuit is basically actually a positive thing.
Yes. Okay. Sorry, why is that?
If your circuit is under constraints, but you still have something that works, then you're basically handling something more general than your circuit, and so it's fine.
I see. Okay. Interesting. But yeah, for the obvious reasons, though, obviously this is very popular in the hardware industry, which is that if they make mistakes on this, a hardware recall is much more expensive than patch.
So actually, another quite important aspect of the hardware verification side of things is also that a lot of hardware verification happens kind of as a black box, where all these hardware people have like Verilog or whatever else they've been using for like 20 plus years. And a lot of these things are not form verification tools, but they do have, like SMT backends and things like this. And so it means you can give all of these things to hardware engineers who don't care or know about form verification, and form verification happens nonetheless. Whereas software is extremely different. Because with software, you give people some language, sketchy compiler, and nothing happens. So there are a lot of differences in the kind of hardware and software verification models. And people used to think that software verification would be solved if you were in Cambridge. There was Mike Gordon, who was one of the early people doing software verification, switched from software verification to hardware verification in the 80s because he thought software verification was about to be solved. And then instead he solved hardware form verification, and software verification is still a nightmare. So there's a lot of like interesting things going on in hardware, but there are a few actual parallels between hardware and software in that sense. The tooling is very different, the problem space is very different, and the size of the space that you're looking at is very, very different.
Okay. So presumably the execution clients that participate in the network will probably not all be running on verified hardware, but that could be okay if enough of them are running on verified hardware.
Well, everything is run on verified hardware or like production.
If you have
an x86 CPU, it's or x64, it's formally verified.
Yeah.
Oh, well, that's good news.
That is good news.
the one which is not fully verified, like all these like shit.
Chinese boards.
But to be clear, we are actually, what we're doing with respect to the actual EVM client is what we're checking is that when you're interpreting the EVM bytecode to RISC-V, that RISC-V bytecode executes the same, produces the same outputs on the same inputs as would a formal semantics of the EVM. And we're doing this because we're just looking at the RISC-V assemblies independent of the source language for the EVM client. It's just tedious because you're doing proofs about RISC-V assembly, which is a bit of a nightmare. So then you can write your client in name or Rust or something else, and it's enough. You just have to be able to compile to RISC-V.
So would the execution clients then be required to run on RISC-V?
Well, they will for ZKVM.
They will, because they're going to be running inside a RISC-V ZKVM. So all ZKVMs that are participating, all execution clients that want to participate in L1 proving need to be able to be compiled to RISC-V somewhere, right? Which the Nethermind client now can. so adding a quick add in there. So, is this making sense?
Okay. So the execution clients, for the purposes of this discussion, are running on a ZKVM.
Yes, they are. Right. Well, I mean, no one is. I mean, RISC-V hardware hardly. I mean, it exists, but it hardly exists. Right. It's not very easy to get. So we're not assuming that people are going to have RISC-V machines to be running this in any kind of way. But it will be running on the ZKVM, and then, of course, actually, the correctness of the VM itself is sort of, as we said, looking at looking at the previous diagram, right? The correctness of the VM itself is sort of in the witness generation, right? And like the trace that it executes. But even if that's not correct, as long as the constraints are verified against formal RISC-V semantics, that's kind of fine because, the prover would accept it, right? If it's correct, and if it's not, certainly if we verify at least the verifier, it will also reject such an incorrect proof of such an incorrect trace. If the prover was wrong, shall we say, too. So if I'm making sense here.
Yeah, I believe so.
Excellent. If you believe in it.
Sorry to ask yet another question. Wait,
I'm just going to mention for the record that I was planning to be about like 5 minutes in by the time I got past this slide.
I told him yesterday, he's like, oh, what am I doing? I was like, it's all about compilers.
Yeah.
No, but Lee, I just want to ask now about the
Sure, please. Go on.
running an execution flash on a ZKVM. Like, I suppose that makes sense on some level, but like.
Well, yeah, I mean, it is a strict requirement. You have to commit to it.
Yeah, but normally the client would be like a long running process, and the ZKVM is going to produce a proof at the end of the program execution.
Well, what's usually done is you run your client for one block.
Okay, so you.
So it runs the execution for a full block, and then it like certifies the proof certifies the execution for the whole. The state update that corresponds to the execution of the whole.
Well, that makes sense. I just assumed like the normal client that would be running 20%.
Yeah, sure. But here we just run it to verify the state diff for a single block. Yeah, makes sense.
Yeah, yeah.
Cool. Okay. Cool. Okay. So now I wanted to go on a little bit to the verification of the constraint systems and witness generators, right? And so the first thing that I wanted to talk about is the fact that, well, there are basically two ways of writing these constraint systems and witness generators, right? Which have somewhat different profiles with respect to what it means to formally verify them and what can be formally verified about them, right? So there is obviously the ZK EDSL direction, like pq2 and Halo 2, that obviously embeds a ZK DSL into an existing language, typically, well, in both of these cases, Rust, but there are also things like Gnog, which embeds into Go, and these sorts of things, right? And there, obviously, there are a bunch of pros. So obviously, you can use the existing compiler toolchain and all of these sorts of things. You can use a bunch. You probably have a bunch of libraries in your host language that you can also use. All of these positive things. However, this advantage has a bunch of downsides when it comes to formal verification, right? So, firstly, you basically have sort of two options in terms of verifying some like constraint set within the ZKDSL, which is either you need to have a full model of the host language, right? Or you need to instrument the ZKDSL. And this is the direction that my team has gone for a bunch of things, at least for the moment. So, for example, for pq2 and Halo 2, we have instrumented versions of the ZKDSLs where, like, the functions that generate extra constraints are also have basically an instrumentation that also keeps track of these, and then at the end can extract these into lead, essentially, right? And so obviously that has some impact there, which is obviously in the instrumentation direction. We need to trust the correctness of the instrumentation, right? So we could have made a mistake when writing the instrumentation that extracts us into lean. Often, without being able to reason about the full language, we're not really going to be able to reason about the witness generator, right? And so, and I'll talk a bit about some options where you can in a second. And then, of course, it's also the case that you kind of have to trust that the constraints are deterministically generated. I don't mean the constraints are deterministic in the sense of like a deterministic ZK circuit. I mean that every run of the constraint generator will always generate the same constraint set, right? Because otherwise, obviously, you would be formally verifying potentially against against a constraint set that may not be used for every single run in practice, right? So that's an extra like dependency that you have to add in the case of instrumentations, which is suboptimal. And the ZK DSL, and then you have the DSL route, where you actually use a specific domain, like you actually create your own domain-specific language for this, like CirCom or Zergen, right, in the RISC-0 case. And these basically have kind of the opposite pros and cons profile, right? In that, well, you have to develop your own tool chain, you need to write all of your own libraries from scratch, etc., right? However, it's easier to extract because, well, typically your DSL will have will be relatively simple, have a well-defined AST, well-defined semantics, etc. And so it's fairly easy to write a full model of the syntax and a sort of like full model of the underlying semantics. And in fact, so we worked with RISC-0 to create a model of Zergen, And in fact, we've embedded, so this is actually, to be specific, Zergen v1 that we worked with. Now there's a Zergen v3, which hopefully we'll be working on at some point in the not too distant future. But yeah, so essentially there, in fact, and this is a very cool feature of Lean specifically, which is it has this sort of elaboration step before the, like it has a first elaboration step in Lean, which allows you basically, which can be arbitrarily programmed at within the language, right? Within the language itself, and so you can basically actually arbitrarily embed syntaxes into Lean. And in fact, what we have for Zergen, you can actually just basically copy and paste Zergen code into Lean, and it just knows what that means, right? It will automatically pass that into an AST, and you'll have an AST that you can reason about. That's also the case for our Yule model, right? So you can actually copy and paste Yule with the right libraries included. You can copy and paste Yule into Lean, and it will just automatically pass that into an AST for you, right? And then we have, like as I said, like a full model of the semantics of this. And also in the case specifically, not so much of Circom, but at least in the case of Zergen, it describes both the witness generator and the constraints generator within the same DSL. And so we can basically get we can get models of both of these things, and then we're able to prove soundness and completeness of the constraint system against the witness generator and vice versa, right? Which obviously primarily, obviously, this is primarily useful for proving liveness properties, because as we said, just knowing that your constraint set implies your specification is enough for safety properties. But but certainly if you want to know, if you want to have liveness, you probably want to know that your constraint, your witness generator is always going to generate witnesses that satisfy your constraint system, right? Cool. Yeah, I think those are most of the points here. Any questions on this?
Just one regarding, for example, Plonky 3, right? When you talk about the constraint system, like, for example, in Plonky 3 with the airbuilder that you have, that you use them to construct your airbuilder.
Yeah.
Like, in principle, you can have like a symbolic airbuilder. Right?
Yes. Oh, we do. In fact, that's how this works. So, yeah, that is exactly.
I was about to say, like, if you have like a symbolic airbuilder, then you could use that symbolic route.
That is exactly how this works. So you can go on to, yeah, so if you go on to, we have a Plonky 3 fork on the Nethermind ETH GitHub, and you can go look at this. And yeah, we have some simple demos working for the moment. One obviously also issue of the ZK DSLs, which you've just reminded me of, thank you, is that every single company makes their own flavor of these ZK DSLs, unfortunately. So we've tried to write these in such a way as to be as generic as possible. So that, and in fact, we've now worked with two different ZK VMs that use their own Plonky 3 flavors, and we were able to adapt their in-house Plonky 3 flavor to extract within the space of a day or two, essentially, right? So we've written it in a way that's generic enough and really actually kind of serves, as you said, using sort of like symbolic builders and these sorts of things. That mean that really, to a large extent, we can basically do almost drop-in replacements. We also have like a Rust trait that sort of describes interactions with permutation and lookup arguments, right? So you can write these sort of in an abstract way so that we can extract those. And then obviously this allows us to then extract multiple airs and reason about their interactions. And this is very good in terms of modular reasoning, right? Because now a lot of ZK VMs particularly have an architecture where there are essentially there is typically like a decoder which decodes a given instruction, fetches some basic information, and then really like references a bunch of other airs that really do the computation. Right, essentially. So this is a very common architecture in ZK VMs these days. And so by allowing us to extract on an air-by-air basis like this, and then being able to extract the permutation or lookup constraints between these different airs, we're then able to actually verify things in a very modular way, essentially. Right. Okay. Yes, okay, so giving some ideas of sort of real-world extractions that exist out there, right? I mentioned a couple, so we've developed this Halva, and I actually am missing one, the Ray Labs extraction. But anyways, Yes, yeah, okay, so I'm missing one in this list as far as I'm aware, possibly more, but yeah, so we have an extraction from Halo 2 into lean, Plonky 3 into lean, R1 CS constraints into lean, right? And then we have, as we said, generic like air models, permutation lookup, logup models, as well as sets of relevant theorems and lemmas, as well as this finite field extraction and proof reconstruction that allows us to then easily, well, hopefully easily write proofs about this, the resulting extracting constraint system into lean. The FF extraction and proof reconstruction, just for context, is there is an SMT theory called an SMT theory for finite field reasoning, which basically uses Grosvenor solving essentially through CBC, the CBC5 SMT solver. It calls it something called cocoalib, and we have actually written our own fork of CBC5 that allows us to actually extract this these Grosvenor reductions, and then so basically we're actually able to fully reconstruct these proofs into lean. Right, so that we don't even have to actually trust the Grosvenor basis solver. A couple of issues with this for the moment is, in the future, CBC5 itself is going to add proof extraction for the finite field SMT theory, which is going to be good because essentially lean already has lean SMT, which allows you for the existing like theories that allow for proof extraction on SMT solvers. It already allows you to reconstruct these proofs in lean, essentially. But the CBC5 doesn't yet extract the finite field theory. So, but when this is the case, we'll be able to fully integrate our work into the existing lean SMT, and then you can have queries over sort of multiple theories, right? So you can have queries that range over constraints on finite fields, but also natural numbers, ADTs, these sorts of things, right, which are permitted by this proof extraction. So that will become much more powerful in the future because, in a sense, we kind of got a little bit overtaken here because there's a new tactic in lean called, well, relatively, it's a few months old, but this came up while we were working on this, called grind, which itself actually has a built-in Grosvenor basis solver, right, that already does a lot of this. But one of the key advantages is obviously cocoalib is a highly optimized C++ implementation of Grosvenor basis solving. So we can actually solve some slightly larger examples than grind is able to. So grind will time out on a lot of these examples where we won't. Although because we have an external call to CBC5 and the tactic is still not highly optimized, there's some initial high fixed costs to creating another thread and running CBC5, which means that for shorter queries, grind can be considerably faster. But we're working on improving that in the future, right? And as I said, certainly once this gets embedded into the broader SMT, we have full proof extraction for finite field into the whole SMT lib proof calculus essentially. Will then be able, with the power of this tactic will be increased quite a lot. Cool. So as I said, we have these sort of extractions into lean. This one is a little bit special in that, as I said, Zergen here is a ZK DSL rather than a ZK EDSL, so we can extract both the constraint system and the and the witness generator into lean. And so we were able to actually prove soundness and completeness of these witness generators against the constraint system and vice versa. And in fact, actually, so in our work on RISC-0 v1, we formally verified, I think, a bunch of small circuits, but most importantly, once again, Iliad's hard work on bit vectors paid off because we were able to fully formally verify the instruction encoder of RISC-0 against the spec that we extracted at the time from the sort of natural language specification of RISC-V, right? Now, of course, in lean, thanks to the hard work of Galois and Lindy Labs, as well as Cambridge, I think, also participated.
A lot of Cambridge. And Edinburgh as well, actually. Okay.
Thanks to the efforts of a bunch of people. So we now have a sale to lean extraction, which is complete enough to support the full extraction of the RISC-V, the formal RISC-V sales spec. which is sort of meant to be the epistemological source in the sense that
It's the official one.
yeah, it's basically a RISC-V process. If a RISC-V CPU does not satisfy the spec, well, it's not a RISC-V CPU. This is the meaning of RISC-V, right? And we have an extraction of that into lean, which obviously we didn't have at the time. Then there are a bunch of other tools. So there are two tools, one of which I didn't actually mention here. So apologies to Ray Labs there if you're watching. So without mentioning it verbally. But then yes, there's pq2 by Veridice, which extracts a bunch of different things. So they have a GNOG, a CIRCOM, and R1CS extractor into SMT-lib, specifically the finite field theory, right? And in fact, I mean, this is actually a bit of an oversimplification because, as I understand it, there are a bunch of closed source simplifications and these sorts of things which are actually applied to this before it hits the SMT solver, right?
The magic is not actually the SMT solver.
Yeah, exactly. So there's a bunch of magic in this arrow that is not shown because I don't even know what that magic is. They don't tell me.
So they have their own IR and they do
yeah.
a bunch of stuff.
Yes. Well, and we're going to mention LZK in a second. And then the other one that is not mentioned here is that Ray Labs has an extractor from GNOG into lean too, right? But yeah, so one question that sort of comes up very naturally here is, okay, so you've got a bunch of extractors, and it seems that like the ZKDSL, like new ZKDSLs and ZKEDSLs are still coming out, right? And there's no necessary reason to believe that, hey, any of these are in any way fixed. So is it the case that
most of these are not used, right? Like Halve, I guess it's not that useful anymore. So they actually not, and then Zergen also not because they've moved on from Zergen.
Yes, So basically, these three are dead essentially, right? Surveyor was is a toy tool that I wrote over like a weekend. So yeah, Surveyor is very.
But I think beyond that, there are also even other extractions by other teams, through Lean and stuff. So Galois.
Yes, Galois also have their own.
There's Lean and like Lean themselves.
Yeah, exactly. Okay, I'm just going to add as a a qualifier for all of this. I don't guarantee that any lists in this talk are complete anyway, because there are lots of people working on.
And if you're watching in the future.
Yes, and if you're watching, exactly.
Then it's definitely not complete.
Exactly. But the point that I was trying to make here is, of course, there are, as I said, just evidenced by the fact that a bunch of these things are essentially already dead, right? You might think, hey, isn't there some space here for an intermediate representation of some form that can both be extracted into a bunch of different constraint systems, right? Different arithmetizations, but also allow us to actually reason in a unified way on this, right? So one like very nice way of doing this might be of writing extractions from all of these into some intermediate representation, which then has a bunch of extractions into, as I said, different arithmetizations, but then also has extractions towards a bunch of formal verification tools like extractions into lean, other proof assistance, and SMT solvers, right? And in fact, this is something that, once again, I think that Veridice has been working on, and this is actually the IR intermediate representation that pq2 uses called LZK. So
pq2 used to have its own IR.
Oh, okay. But as I understand,
now it also runs on an LZK.
Oh, okay.
They had their own IR previously.
Oh, I see.
And then obviously some of the good bits of that IR made it into LZK. So
yes,
in some sense, part of that LZK
is inspired. Yeah. Okay, cool. So there is this LZK IR which has now been open sourced, and pq2 also is able to support this and extract it into SMT-lib to be able to verify some simple properties about it. But
actually, on the SMT bit, even better than that, the plan is actually that there is an SMT MNIR dialect. And so the idea is actually to take the MNIR dialects we have and then lower those to the SMT dialects.
Oh, really?
And move through that, because then it gets much easier to add new dialects and still have that lowering to SMT.
Yes, I see.
Rather than an actual encoding to SMT.
That makes sense.
Which is another Tobias bailing me out with a paper.
Oh, nice.
Type of situation.
There you go. Yeah. Okay. So anyways, there is this sort of like universal zkIR in quotes that is being developed, and that there is also a lean model of this being developed, as I understand, right? I think.
Yes, started 2 weeks ago this week.
Okay, there you go. So Paradise has started working on the lean model of this IR.
I'll say it's Cambridge and Galois mainly.
Okay, there you go. As you can see, Alex has a lot more of these details than I do. So because really, I'm trying to give a talk here on a what do you call it? On a program, a research program, which is actually led by Alex. So there you go. I'm actually kind of
There's
curious.
a lot of things happening.
There's a lot of things happening, and I've tried to resume as best as I can. And there are certain moving parts which I'm not fully, which Alex has more familiarity with me clearly than me clearly. But yes, anyways, try my best in the context. But yeah, so anyways, this CKR exists. It's going to be hooked up to, so there'll be a formal model in Lean. There'll be extractions into SNTlib. And that means that, and then also they're going to be developing extractions into all sorts of arithmetizations. But of course, this is going to be an ongoing process, and that, well, we've participated a little bit in the discussions on what should be on the design of LZK, because in particular, when we were working on our Plonky3 extraction, so LZK came up started being a thing during this process, and we were thinking of basically just extracting from Plonky3 into LZK, and then basically just building an LZK. Sorry?
It was not ready.
Yeah, it turned out, shock. And then extracting LZK into Lean, and it turned out that it was not ready. And in particular, Plonky3 uses a lot of flavors of Plonky3 uses logup arguments, and logup arguments specifically allow you to set you have to set the exact multiplicity of all the values in your shared bus and these sorts of things. And there was just no way of modeling that in LZK at the time.
So
now I believe there is.
I think it was merged last week.
Oh,
they merged something last week, and actually they wanted feedback about if it was enough for you.
Okay, well,
we can look at that in the break.
Excellent. Well, we'll get back to them in the coming days. So there you go. Thank you for the update too. So there you go. Until recently, this CKR was missing some features that we kind of needed for what we wanted to do with Plonky3. So we ended up actually just going directly to the lean extraction as we'd sort of originally intended, right? So
one of the interesting points actually about the lean extraction is, which might be relevant because we have some compiler people in the room.
We do.
Is that something that hurts proof ergonomics a lot? Is that at the moment when we do these lean extractions, most of them are kind of done in it. And naive is maybe not the right word, but basically you read off the constraints from the ASC, and then you unfold all of these constraints in Lean, which lacks a lot of structure compared to the way that the circuit is written. And this is visible when you try to write the circuit in Lean itself, where you have a lot of structure and much simpler proofs. And so an interesting question, which relates to the compiler aspect, is what would be the best way to actually get, structured constraints from, if not the ASC, something else from the compiler to be able to extract it into Lean.
Okay, so I have kind of a out-of-the-box suggestion about this. I'm not convinced that it's good, but I'll throw it out there. The thought is that rather than having manually constructed the constraint system in something like Plonky3 or CIRCOM, we take a description of the semantics of RISC-V, maybe this one that exists that was mentioned, or maybe in a different one in some DSL that's more amenable to this use case, and we generate from that the constraints in a way that it's an automated way that is creating the structure that Alex is referring to.
So this would be virtual RISC-V circuit, something like using the RISC-V spec.
Yeah. So I've done some R&D on this type of approach before. I found.
So we were planning on, well, not RISC-V initially, but we do further the event with the key. One of the milestones is to basically do a minimal VM, and so that would give us a taste of what it looks like.
So I did some R&D on this type of approach. I found a subset of predicate logic that's equivalent in strength to Halo 2 circuits, and I made a compiler which can go from predicate logic to Halo 2 circuits. So the advantage of an approach like that, well, one of the advantages anyway, is that you no longer have the problem of verifying in an ad hoc way that the constraint system is correct. You just sort of need to look at the predicate you expressed and make sure that it's the right predicate. And then you get that the circuit is right out of the circuit compiler being right. I think the major issue with this approach for something like this use case of the ZKVM is that the circuit that you get is probably not going to be as optimized and parsimonious as a manually generated circuit. And so it could take like 10 years of R&D or something like that to actually get to the point where you have like a circuit with the type of efficiency that is required.
Yeah. So this is a good question. So have you seen the arithmetization of first order logic paper?
Well, yeah, I actually, my research predates that.
Yeah.
It's a little more technical than that.
But I think so. I'll use that because at least it's kind of public to there's a reference. So there's this paper which shows you can basically come up with an arithmetization of first order logic, and the encoding is like fairly simple, where obviously you have like enough encoding from like an AND to a constraint.
Yeah.
Now the thing is, like you say, it's clear that you can have an efficient encoding of the basic building blocks of your predicates into constraints. It's unclear that obviously when you're formulating your predicates as a whole, you don't end up with something that's too big, which leads to more constraints that you'd wanted, even if the encoding is kind of a priori efficient. But the interesting question is that actually there is quite a bit of research going on with the people who do SMT solving and whatnot into reducing the size of predicates. And so it seems like there's an alternative optimization approach, which is to just throw SMT solvers at this and say, like, here's what I have, just reduce the size of this while proving along the way that, it's logically equivalent. And that would be interesting to explore. But actually, I'm curious, did you have your work working over a specific finite field or arbitrary finite field or something? Because obviously the arithmetization first order logic paper was written by this guy.
Murdoch, yeah.
Yeah, Murdoch. Yeah, so I actually know him because he lives in Edinburgh.
Yes. He also wrote the first, what was it, Skyro compiler? I remember,
something like that.
Yeah, it was a proof assistant to Cairo. Oh, Idris. Idris, yes, it was an Idris to Cairo compiler.
So I'd actually met him.
He's quite a character, actually.
I actually had met him long before I realized that he was writing this paper, and we only realized because we bumped into each other in Berlin in June.
Oh, okay.
You happen to also work in this industry.
I see.
But anyway, the thing is, in his paper, he's targeting the constraints are over the rational numbers or something.
I see. Yeah.
Because he's obviously not a cryptographer.
Yeah.
He's just I have people doing constraints in a paper about this.
Yeah.
And so I think there is actually potentially quite a bit to explore in that. The other interesting aspect, which we looked a bit into this, was then when you're trying to write obviously your circuits for a program, let's say, then obviously you have to translate your program to that logic. And that requires some amount of expertise.
Yeah, I think when you're trying to prove a program correct, you would write, maybe the predicate that you're trying to express with this program, and then you have the problem of proving that program implements that predicate. So yeah, it does require particular expertise, but I think it's beneficial because you save an entire step of having to prove the program correct.
Yeah.
I think, and I actually, implemented in software this translation method from predicate logic to circuits, and so I found that there are some major issues that you're likely to run into when doing something like that. Generally, around the polynomials just turning out to be way too large. And I think
so. Number of constraints. At least when I did some examples by hand for the arithmetic first order logic, the degree of the constraint was okay, it's just the number of constraints we get was insane.
Right, you could either have too high degree or too many constraints. And you know, I made some progress on addressing that, but not all the progress that needs to be made, I think. And I think the other issue with like Gabe's work in specific as applied to this is that it only does first order logic, and I don't think that's
So you should be able to do higher order logic pretty much the same way.
Well, yeah, I did do a version of second order logic, and that does work. I don't think that it would work very well with polynomials as the target, but I did it with Halo 2 circuits as a target, and that worked fine because there's actually, you know, I actually was able to show an equivalence, at least in my own mind, show an equivalence between the version of second order logic that I arithmetized and Halo 2 circuits. So I think there's something natural there.
Yeah, that makes a lot of sense. That makes a lot of sense. And in a sense, actually, as part of the Risk Zero tool, we were kind of doing something a little bit related in the sense that we were, whenever we had our extracted arithmetization, we had basically like a simplification, a sim set that we would always apply to it, which would automatically simplify it into a much smaller set of constraints, right? Which obviously is doesn't have the generality, but also does
But can you say more about this? Because otherwise, surely they would want to upstream having that smaller set of constraints.
Yes, yeah. So the thing is, it wasn't only it wasn't only like constraint simplification itself. It was also actually like moving it a little bit into the ambient like lean terms, right? So it was in a sense a little bit of the opposite in that it was taking a constraint system and trying to reconstruct from it something that looked more logical, right? Essentially. And so, for example. Like the example that always comes to mind is the like is0 example, which in like as a ZK circuit is you know, relatively straightforward in that basically you say, hey, well, either you assert that either this thing has an inverse, in which case it's non-zero, or doesn't, in which case it's zero, right? It's sort of how this works. And with the constraint set that we extracted, by running the sim set that we had on it, we basically actually just got an if. We basically just got like a very simple branching on like, hey, does this thing have an inverse? And from there, we were very easily able to say, well, like from lean, we know that like the finite field theory tells us that something has an inverse if and only if it's zero. And then like basically with like 2 rewrites, we got the spec we wanted. So it's a little bit kind of like the opposite of that, a little bit.
That's very interesting.
Yeah. But I mean, there wasn't too much, there wasn't really any secret sauce to this. It was just, you know, some, I'm not going to say that we did this in any way in a systematized way. It was literally like, as we went along, we found that adding this to the sim set was useful. And so it was developed in a very like ad hoc manner, but it worked out working fairly well in practice. And this is open source, so you can have a look at it yourself, if you so desire.
That could work. Like take like for example the constraints for risk zero and show, you know, through a series of simplification steps that it implies the predicate. Which
yeah, and in fact we got an if and only if with the so we actually had a really interesting simplification engine which I hadn't planned to talk about, and we're now over time for not only what I was meant to say but the whole session. But I'm going to say it anyways. So if anyone wants to leave, feel free to do so. As I always say when my talk's over on. So, but I will continue talking. So there you go. But essentially, we with the extracted Zergen, we did a bunch of interesting things. Where firstly, we would actually, because when we ended up extracting sometimes fairly large circuits into lean, right, and then trying to simplify them, we ended up with some issues where we would get timeouts because the terms generated would be so huge, right? So the first thing that we did is we did basically like some circuit partitioning where we would cut up the constraint systems automatically into subsets of them, right? We would also do reorderings of the generated Zergen to minimize the lifetime of every variable, right? So we would basically like move like the creation of like a new value as far forward in the Zergen as possible, right?
and we would use its we would push its last use as far back as possible, and then we would even insert explicit annotations into an extension of Zergen that told the underlying semantics you're not going to need this anymore, right? And so this basically minimally created an underlying state that was minimally complicated. And in fact, this essentially compilation step, it was a very simple compilation, but this compilation step was a certifying compilation step, in that it would simultaneously generate a proof that the original Zergen is semantically equivalent to the simplified one, right? At that point in time,
which is why you're able to treat them as a subtype or something.
To treat what as a subtype, sorry.
When you're refactoring them, can you treat them as is there some fancy way to treat them as a subtype?
No,
I don't think that's what you're doing.
Not really. We could.
But then you would automatically carry your proof.
Yeah. You could. We didn't. In practice, we didn't. Right. So we just generated a separate lemma that just said that would just show that hey, the semantics of these two things are equivalent, right? And this was completely automatically generated. And then for each one of these blocks, we would then basically just unfold the semantics, apply so we would generate the constraints or the witness generator that was equivalent to this. We would apply a simplification set, and then we would sequence all of the specs for each one of the sub-circuits we created, and then re-simplify again, right? And as I said, with this, we were able to, for a bunch of fairly non-trivial circuits, get things that were generated completely automatically, generate a proven specification, weakest precondition style specification that was already very close to the desired spec.
Okay, so we have two directions we could go to sort of accomplish the same thing. I guess the pro of going from the circuit to the stack is that you don't have to try to make a compiler which is sophisticated enough to generate an efficient circuit. And the con of that approach would be that there could just be immense computational complexity.
Yes.
Okay.
Yeah, exactly. Cool. Okay. So since we're massively over time, I'm just going to say one more thing, and then I'm going to let Kwang do all of the proof system talking later.
Are we massively over time? 6 minutes over time now.
So it breaks now.
Yeah. So we're not horribly over time.
We're not horribly, but we are.
Yeah.
But so what I'm going to do is I'm going to speak a little bit about our work on RISC-V, verification of RISC-V specifically, circuits specifically, just a tiny bit. And then, as I said, the proof system stuff I will let Kwang talk about mostly this afternoon. I think you were going to do that anyways, right? So I think this is kind of fine. But yeah, so to give you some interesting sort of outcomes from all of this work, right? Because I've talked about some relatively simple stuff we've done in the past with RISC-0, but with particularly, so there are two RISC-V ZKVMs, one of which unfortunately I can't name, but some people in the our NDA is very soon going to stop being a thing. We're making the announcement in a couple of days, but I'm not allowed still to mention the name. But we've worked with two big RISC-V ZKVMs, one of which is succinct. And we have basically verified in their case, we verified all of the ALU chip, right, against the formal RISC-V semantics. So basically we have the constraints for the ALU chip 100% are 100% proven against the formal RISC-V semantics. And then for the other ZKVM that I cannot name, but definitely exists. This is not in my imagination. Sorry. Exactly. Yes, the huge LWK. Exactly. But we've worked with another ZKVM where we've gone even deeper. We have verified all of the ALU against the formal RISC-V semantics, and we've also fully verified the memory argument, assuming basically the semantics of the lookup argument that underlies it, essentially. And so that is virtually now 100. That one is virtually 100% verified, other than the take up and put down code as well as the system calls. But we're looking at also doing that in the future. But yeah, basically.
The system calls are probably going to change anyway.
The system calls are, and obviously also pre-compiled. Sorry, pre-compiled. That's important.
Yes, but it's both the way that the pre-compiled are handled via
exactly,
and the way the systems
exactly.
are done will change.
Exactly. So the thing is, anyways, these parts of the system are kind of like not stable enough really to be verified at this point in time anyways. But essentially, there is a zkVM there, which is out there, that shall not be named, that has basically almost reached the standard required in terms of constraint verification for L1 proofing. So one company, who will be announced in the next couple of days, has reached that standard already. Cool, and I think I will finally let you all be free and go and have some food and these sorts of things. And you'll hear some very interesting things from Kwang this afternoon.
And we're in this room again.
Sorry, and we're in this room again. Okay, excellent, perfect. Thank you so much for listening, and thank you also for all your contributions. This ended up being a very interactive session. As I said,
this is the goal.
Yeah, sure. I was expecting all of it like to talk for like 20, 25 minutes and then have interactive questions, but it ended up not being like that. But actually, I think this was actually a more interesting outcome. So thank you all so much for your participation.